What is time, really? A sleepy science story. Let's know about the river that never stops flowing. Time moves like water, sometimes a trickle, sometimes a flood. You dip your fingers in, but the current slips away. Where does it come from? Where does it go? And why does it only move in one direction? Imagine standing at the edge of a wide, slow-moving river. The water is clear enough to see the pebbles below, each one smoothed by centuries of gentle friction. You crouch down and let your fingertips break the surface, feeling the cool slip of the current against your skin. For a moment, you try to hold it, to trap a handful of water in your palm, but it drains away, relentless. This is time. Not a thing you can keep, but a force that carries you, moment by moment, toward some unseen sea. The ancient Greeks pictured time as two gods. Kronos, the elder, was the steady, unyielding march of days and years, the kind of time measured in sundials and hourglasses. Kairos, the younger, was the god of fleeting moments, the instant between a breath taken and released, the pause before a decision, the fragile now that vanishes before you can name it. Science, of course, does not speak in gods. But in its own way, it tells a similar story. Time is not just a measurement. It is a dimension, woven into the fabric of the universe as deeply as length or weight. And yet, unlike space, you cannot wander through it freely. You cannot go backward. You cannot even stand still. Why? Think of a drop of ink falling into a glass of water. At first, it is a dark, concentrated swirl. But slowly, inevitably, it spreads. The particles drift apart, dissolving into randomness. No matter how long you wait, the ink will never gather itself back into that single, perfect drop. This is entropy, the universe's quiet rule that disorder always increases. Time moves forward because energy always disperses, because heat always flows from warm to cold, because every shattered cup, every fallen leaf, every every breath you exhale is a tiny part of this great, irreversible scattering. The arrow of time flies in one direction because the universe is slowly unraveling, like a thread pulled loose from a tapestry. But what if you could step outside the river? What if, like a heron lifting from the water's surface, you could see time from above? Einstein's theory of relativity whispers that time is not as rigid as it feels. Near a black hole, where gravity bends space like a heavy stone sinking into a mattress, time stretches like taffy. A clock ticks slower there than on Earth. A traveler moving at the speed of light would age mere seconds while decades passed for those left behind. Time, it turns out, is not a single, universal current. It is a network of streams, each flowing at its own pace, twisting around stars and galaxies in ways that defy intuition. And yet, for all its flexibility, time never flows backward. Memory lets you revisit the past, but only as an echo. The river carries you forward, even when you long to linger in an eddy, even when you strain to see the shore you've left behind. Close your eyes now, and listen. Beneath the silence, there are rhythms. Your heartbeat. Your breath. The slow blink of your eyelids. These, too, are ways of measuring time, not in minutes, but in pulses. Your body is a clock, its gears turning in the rise and fall of your chest, the firing of neurons, the silent division of cells. Even your DNA keeps time, its telomeres shortening like the burning of a candlewick. But time is not just inside you. It is in the world beyond your skin. The moon pulls the tides, and the tides mark the months. Trees grow rings, each one a record of sunlight and drought. Continents drift, glaciers melt, mountains rise and crumble, all of them keeping time on a scale too vast for you to feel. And beyond Earth, time moves in even stranger ways. A photon racing from a distant star may take millennia to reach your eyes, so that when you gaze at the night, you are not seeing the present, but a mosaic of the past. Some of those stars may already be gone, their light still traveling toward you like a letter written by a hand long turned to dust. And yet, for all its mystery, time feels intimate. It is the space between a question and an answer, between a touch and its memory. It is the reason you can grow, learn, love, because each moment is new, because each second is a door that opens only once. But who set the river in motion? And what if, somewhere in the cosmos, time dances to a different rhythm? That is a question for another night. But who set the river in motion? And what if, somewhere in the cosmos, time dances to a different rhythm? That is a question for another night. Chapter 2. The Cosmic Clockwork. The universe keeps time in ways we barely notice, the spin of planets, the pulse of stars. Even your heartbeat is a tiny echo of this grand rhythm. But who wound up the clock? And does it tick the same everywhere? You're lying on your back in a field of tall grass, the earth still warm from the day's sun. Above you, the sky is turning, not quickly, but with the inevitable certainty of a breath being drawn. The stars appear fixed, yet if you watch long enough, you'll see them drift. Orion's belt tilts westward. The North Star traces a slow circle. This is the first clock humanity ever knew, the great wheel of the heavens, turning as Earth rotates beneath it. But this clock is far older than humanity. It began ticking long before the first life stirred in primordial oceans. The universe has always kept time, not with gears and springs, but with the motions of celestial bodies, the vibrations of atoms, the expansion of space itself. Every planet spins like a top. Every star pulses with energy. Even galaxies rotate, their spiral arms turning over epochs so vast that human history is but a blink in comparison. Consider our own solar system, a collection of worlds bound by gravity's embrace. Mercury races around the Sun in just 88 Earth days, while Neptune takes 165 years to complete the same journey. These orbits are so precise that we can predict planetary positions centuries in advance. The same gravity that pulls an apple to the ground keeps planets in their tracks, their movements as regular as the swing of a pendulum. Yet this clockwork isn't perfect. The moon's gravity tugs at Earth's oceans, creating tides that act like brakes on our planet's rotation. 100 million years ago, a day was just 23 hours long. Dinosaurs experienced sunrises coming quicker than we do. Mars, smaller and less massive, has already slowed significantly, its days lengthening over eons as its rotational energy dissipates into space. Even Jupiter's great red spot, a storm that has raged for centuries, is gradually shrinking, its winds slowing like an old clock running down. What set all this in motion? Close your eyes and imagine a nursery of stars, a cloud of gas and dust collapsing under its own weight. As it shrinks, it spins faster, just as a figure skater accelerates when pulling in their arms. This is the conservation of angular momentum, a fundamental law written into the fabric of reality. The young sun formed at the center, while the remaining material flattened into a disk that would become the planets. Each world inherited this spin, this primordial rhythm that continues to this very moment. But timekeeping in the universe goes far beyond simple rotation. Deep in space, there are clocks of astonishing precision. Pulsars, the dense, rapidly spinning cores of dead stars, send out beams of radiation with such regularity that their pulses can be predicted to within microseconds over decades. Some rotate hundreds of times per second, their surfaces moving at nearly a quarter the speed of light. These cosmic lighthouses are so accurate that astronomers once considered using them as navigation aids for interstellar travel. Then there are the quantum clocks inside atom. Cesium atoms vibrate exactly 9,192,631,770 times per second, a rhythm so consistent it defines the modern second. These vibrations are the heartbeat of atomic clocks, which can keep time without losing a second over millions of years. Even more remarkably, this atomic ticking is affected by gravity. A clock on a mountain top runs slightly faster than one at sea level, because time itself flows differently in stronger gravitational fields. This was Einstein's revolutionary insight: time is not absolute. It's a dimension that bends and warps, shaped by gravity and motion. Imagine two identical clocks, one placed aboard a speeding spacecraft, the other remaining on Earth. When the spacecraft returns, its clock will show slightly less time has passed. This isn't a mechanical error, time literally moves slower for objects in motion. GPS satellites must account for this effect, adjusting their clocks to stay synchronized with ground stations. Even your head experiences time marginally faster than your feet, because it's farther from Earth's gravitational pull. The universe's timekeeping grows stranger still when we consider its beginning. The cosmic microwave background, the afterglow of the Big Bang, shows us the universe in its infancy, when it was just 380,000 years old. From that moment to this one, approximately 13.8 billion years have passed. But what does that number mean when time itself was born in the Big Bang? Could there have been a before? Most physicists think not, that time as we know it began with the universe's expansion. And what of time's potential end? Current observations suggest the universe will continue expanding forever, growing colder and darker stars burn out and matter disperses. In this distant future, time may become meaningless, no change, no events, just an endless twilight. Some theories even suggest time could cease to exist at the quantum level, its flow breaking down into discrete, frozen instants. But these are thoughts for another night. For now, feel your own place in this cosmic rhythm. Your heart beats about once per second, a frequency determined partly by the size of your body, just as a planet's orbital period depends on its distance from the sun. Your cells divide on schedules written into your DNA. You breathe about 12 times per minute, a rate that changes with activity, just as a star's pulsations vary with age. You are both a timekeeper and time's passenger, moving through a universe that has measured itself in rotations and vibrations since the first moments of existence. The same forces that spin galaxies course through your veins, connecting you to the great clockwork of the cosmos. And yet, what if time is more than just measurement? What if it's a fabric that can be bent, folded, even torn? That is a mystery for the next chapter. And yet, what if time is more than just measurement? What if it's a fabric that can be bent, folded, even torn? That is a mystery for the next chapter. Chapter 3. The stretching fabric of spacetime. Einstein imagined time as a fabric, bending under the weight of stars. What if you could step on that fabric, sinking into a slower stream of moments? Would you age differently? Would yesterday still be waiting for you? Imagine the universe as a vast, silken tapestry suspended in nothingness. Every star, every planet, every speck of dust creates tiny dimples in this fabric. The heavier the object, the deeper the depression it makes. Now picture yourself as an ant walking across this tapestry. Where the fabric dips, your path curves. Where it stretches tight, you move faster. This is spacetime, not just space, not just time, but a living, breathing fabric that bends and warps under the weight of matter and energy. When Einstein first proposed this radical idea in 1915, it upended centuries of Newtonian physics. Gravity wasn't a mysterious force reaching across empty space, it was the natural result of objects following the curves in spacetime. A planet orbiting a star isn't being pulled, it's simply rolling along the contours of this cosmic fabric, like a marble circling the rim of a bowl. But the real magic happens when we consider time's role in this fabric. Near massive objects like stars and black holes, spacetime doesn't just curve, it stretches time itself. Imagine two clocks, one placed on a mountain top, the other at sea level. After a year, the higher clock will have ticked slightly faster. This isn't a mechanical error, time itself flows differently in stronger gravitational fields. GPS satellites must account for this effect, adjusting their clocks to compensate for both their altitude and speed, or your navigation would drift by kilometers within hours. The extremes of this time warping become truly mind-bending near black holes. Picture an astronaut falling toward a black hole's event horizon. To a distant observer, their descent would appear to slow down, their signals becoming increasingly redshifted until they seem frozen at the horizon. Yet for the astronaut, time would feel normal, they would cross the horizon in finite time, though their fate beyond that point remains one of physics' great mysteries. This stretching of time isn't just theoretical. In 1971, scientists flew atomic clocks on airplanes around the world. Compared to clocks left on the ground, the traveling clocks showed measurable time differences, exactly as Einstein's equations predicted. Even your head ages slightly faster than your feet because it's farther from Earth's gravitational pull, though the difference amounts to mere nanoseconds over a lifetime. The fabric of spacetime can do more than just bend, it can ripple. When massive objects like black holes or neutron stars collide, they send shockwaves through spacetime called gravitational waves. These waves, first detected in 2015 by LIGO, stretch and compress space itself as they pass. The detection was so precise it measured changes smaller than 1,000th the width of a proton across a 4-kilometer distance. Each wave carries the fingerprint of cosmic events that happened billions of years ago, a frozen moment of spacetime's violent flexibility. Perhaps most astonishing is how spacetime connects distant points. The mathematics allows for wormholes, hypothetical tunnels through spacetime's fabric that could connect vastly separated regions. While no evidence exists for natural wormholes, their theoretical possibility suggests spacetime might be more interconnected than we imagine. In quantum physics, entangled particles seem to influence each other instantaneously across any distance, hinting at spacetime connections beyond our current understanding. Yet for all its flexibility, spacetime maintains strict rules. Nothing travels faster than light through it, preserving causality. You can't reach back and change the past, no matter how spacetime bends. The universe protects the sequence of cause and effect, even while allowing time's flow to vary dramatically in different circumstances. As you lie here, breathing slowly, consider how you're embedded in this cosmic fabric. Your mass, tiny as it is, still warps spacetime around you. Your movement through time is unique to your position and velocity. The now you experience is your personal slice of this four-dimensional continuum, different in subtle ways from every other now being experienced throughout the universe. We've seen how spacetime bends and flexes, how it connects and ripples. But why does it only flow in one direction? Why can't we step back to yesterday as easily as stepping across a room? That profound mystery awaits in the next chapter. We've seen how spacetime bends and flexes, how it connects and ripples. But why does it only flow in one direction? Why can't we step back to yesterday as easily as stepping across a room? That profound mystery awaits in the next chapter. Chapter 4. The arrow that never turns back. Time flows forward, never backward. Like an arrow shot into the dark. But why? The answer lies in broken eggs, scattered stardust, and the quiet, inevitable march of disorder. You stand in your kitchen, watching as an egg slips from the counter. In that suspended moment before impact, you might imagine, just for an instant, that it could reverse course, leaping back into your hand as if rewound on film. But reality unfolds differently. The egg strikes the floor with a wet crack, its contents spilling outward in an expanding pool of yolk and shattered shell. No matter how long you wait, the mess will never reassemble itself. The pieces won't suddenly leap back together, the yolk won't retreat into its membrane. This simple observation holds one of time's deepest mysteries: why does it only move forward? Physicists call this the arrow of time, and its direction is written into the fundamental laws of the universe. At the microscopic level, the equations governing particles work perfectly well in reverse. Yet we never see broken dishes reassemble or smoke retreating into a cigarette. The difference lies in a concept called entropy, the measure of disorder in a system. The second law of thermodynamics states that entropy always increases over time, creating an irreversible flow from order to disorder, from neat arrangements to chaotic ones. Imagine a sandcastle on a beach. Left untouched, wind and waves will eventually reduce it to a featureless mound. The reverse never happens naturally. Sand doesn't spontaneously arrange itself into turrets and walls. This asymmetry defines time's arrow. When you mix cream into coffee, the swirls eventually homogenize into a uniform brown. The molecules could theoretically unmix, but the probability is so vanishingly small that it effectively never occurs in our universe's lifetime. The early universe provides the ultimate example. Moments after the Big Bang, everything was in an extraordinarily ordered state, energy distributed nearly perfectly evenly. As the cosmos expanded and cooled, that perfect order gave way to clumps of matter that would become galaxies, stars, and planets. Each transformation increased entropy, scattering energy into new configurations. Even now, stars burn hydrogen into helium, converting concentrated nuclear fuel into dispersed heat and light, another step in the universe's long slide toward maximum disorder. Yet here's the paradox: life itself seems to defy this march toward chaos. Your body is a masterpiece of organization, with trillions of cells working in precise harmony. How can complexity arise in a universe tending toward disorder? The answer lies in local decreases of entropy. Living things maintain their order by exporting disorder to their surroundings. Your cells create waste heat and byproducts, increasing the environment's entropy more than they decrease their own. A single candle can illuminate a dark room because its highly ordered wax molecules release energy as they burn, spreading heat in all directions. Time's arrow manifests in our perception as well. Memories only form of the past, never the future. Aging only progresses in one direction. Even our language reflects this fundamental asymmetry. We say, "the vase broke," never, "the vase unbroke." This psychological arrow aligns perfectly with thermodynamics' entropic arrow, suggesting our perception of time's flow is deeply connected to the universe's underlying physics. Quantum mechanics adds another layer to the mystery. At microscopic scales, particles don't strictly obey time's arrow. Quantum events can sometimes appear time-symmetric. Yet when many particles interact, their collective behavior overwhelmingly favors increasing entropy. Some theorists speculate that time's arrow might ultimately trace back to the Big Bang's initial low-entropy state, making our entire experience of cause and effect dependent on that singular cosmic beginning. As you lie in bed, consider how time's one-way flow shapes every moment. The warmth leaving. The gradual deepening of your breath as you relax, even the slow aging of your cells, all are manifestations of entropy's gentle, unstoppable current. You can remember yesterday but not tomorrow because memory itself relies on irreversible changes in your brain's neural networks. Yet mysteries remain. Could other universes have arrows pointing in different directions? Might time's flow be different inside black holes or other extreme environments? And what does it mean that our entire experience of reality depends on this relentless increase of disorder? These questions lead us to consider time's most elusive aspect, the present moment itself. If time flows like a river, where exactly is now? That is the mystery we'll explore next. These questions lead us to consider time's most elusive aspect, the present moment itself. If time flows like a river, where exactly is now? That is the mystery we'll explore next. Chapter 5. The illusion of now. Now feels solid, real, but is it? Light from distant stars takes years to reach us. The past lingers in the sky. The future is already written in the paths of planets. So where, exactly, is the present? You're sitting by a window as evening falls. A candle flickers nearby, its light reaching your eyes almost instantly. Across the yard, fireflies pulse their bioluminescent code, their glow taking mere microseconds to cross the distance to your retinas. Above them, an airplane's navigation lights blink steadily, their photons traveling for a fraction of a second before you perceive them. Higher still, the stars you see tonight left their surfaces years, decades, even centuries ago. The Andromeda galaxy shining faintly in the northeastern sky. That light began its journey when early humans were first mastering fire. This is the first clue that, now, is more complicated than it seems. Every sight, every sound reaches you delayed by the stubborn speed of light and sound waves. When you touch the pages of a book, the electrical signals confirming that contact take precious milliseconds to travel from your fingertips to your brain. Even your conscious experience lags behind reality. Neuroscientists estimate we're about 80 milliseconds behind the physical world, as our brains process and construct our perception of the present. Einstein shattered the classical notion of a universal now with his theory of relativity. He showed that simultaneity depends on the observer's motion. Imagine two lightning strikes hitting a train platform, one at the front, one at the back. To someone standing on the platform midway between them, the strikes appear simultaneous. But to a passenger zooming past at near light speed, one strike will appear to happen first. There is no privileged now that all observers agree on, just individual slices of spacetime that each consciousness experiences as their personal present. This relativity of simultaneity extends across the cosmos. The sun you see is already 8 minutes in the past. If it suddenly vanished, Earth would continue orbiting the non-existent star for those same 8 minutes before going dark. The nearest star system, Alpha Centauri, shows us a 4-year-old snapshot. Every glance at the night sky is a mosaic of different pasts, some stars shining with light from before your birth, others displaying light emitted when dinosaurs roamed. Quantum physics adds another layer of complexity to the present. At subatomic scales, particles exist in probability clouds until measured. Some interpretations suggest reality doesn't fully settle until observed, implying the present may be a kind of negotiation between quantum possibilities and conscious observation. The delayed choice quantum eraser experiment demonstrates how measurements made now can seemingly influence events that already happened, blurring the line between past and present. Your brain constructs its own version of now through a remarkable trick called post-diction. Neural signals arrive at different times. Visual information processes slower than sound, touch faster than smell, yet you experience them as synchronized. Your consciousness constantly edits your perception, creating the illusion of a unified present. Magicians exploit this neural delay. Their sleight of hand happens during the brief window before your brain catches up to reality. The present moment may be even more elusive than we realize. Some physicists propose that time is fundamentally discrete, flowing in indivisible Planck-time chunks of about 10 to the power of negative 43 seconds, a quantum of time analogous to photons being quanta of light. If true, the smooth flow of time is an illusion, like a movie creating motion from still frames. Others suggest time emerges from more fundamental quantum relationships, with the present being a localized phenomenon in an otherwise timeless multiverse. Yet despite these scientific abstractions, your experience of now feels vividly real. The warmth of sunlight on your skin, the scent of rain on pavement, the sound of a loved one's voice, these sensations define your lived reality. This paradox, the present moment being both scientifically elusive and experientially undeniable, may be the most profound mystery of temporal existence. As you prepare to sleep, consider that your now is unique in all the universe. No other observer, moving at any other speed, anywhere in the cosmos, shares your exact present moment. Your consciousness carves out this sliver of spacetime, this ever-moving boundary between what was and what will be. But if the present is this fluid, this observer-dependent, what does that mean for the past? Could traces of yesterday still exist somewhere in the fabric of reality? That is the question we'll explore when we next open our eyes to the mysteries of time. Last lines. But if the present is this fluid, this observer-dependent, what does that mean for the past? Could traces of yesterday still exist somewhere in the fabric of reality? Chapter 6. The timekeepers inside you. Your body is full of clocks, heartbeats, breaths, the silent dance of neurons. Even your cells count the days. But what happens when these rhythms falter? Can time itself feel different inside your bones? You wake to sunlight filtering through your curtains. Before you even check the clock, your body knows, not the exact hour, but the general shape of morning. Your muscles uncurl from sleep in gradual waves, your pupils contract against the growing light, and somewhere deep in your brain, a cluster of neurons no larger than a grain of rice begins its daily reset. This is your suprachiasmatic nucleus, SCN, the master clock that orchestrates your circadian rhythms. It doesn't need numbers or hands to measure time, it listens instead to the Earth's slow turn, tracking daylight through specialized cells in your retinas that speak directly to this neural timekeeper in a language of photons and biochemistry. Your body is a living chronometer, a symphony of biological oscillations. Your heart beats approximately 100,000 times per day, not in perfect metronome ticks, but in subtle variations that form a unique cardiac signature. Your lungs inflate and deflate about 20,000 times daily, their rhythms syncing with your heart so each inhalation slightly quickens your pulse. Even your digestive system keeps time. Intestinal muscles contract in waves called the migrating motor complex every 90 minutes between meals, a cleaning rhythm as regular as a janitor's nightly rounds. At the cellular level, timekeeping grows even more precise. Telomeres, protective caps on your chromosomes, shorten with each cell division, marking biological age like rings in a tree trunk. Circadian clocks exist in nearly every cell type, their molecular gears turning through daily cycles of protein production and degradation. In your liver, these clocks prepare enzymes for food processing before your usual mealtimes. In your skin, they schedule cell repair for nighttime. When UV damage is least likely. Even your fat cells have internal timers that regulate when they release energy. The science of these biological clocks, chronobiology, reveals astonishing complexity. Your SCN doesn't merely respond to light, it anticipates dawn, adjusting hormone levels and body temperature in advance. Jet lag occurs because your peripheral organs, liver, kidneys, pancreas, resynchronize to new time zones slower than your brain. Night shift workers often develop internal desynchrony, their master clock trying to follow daylight while their organs operate on a different schedule, leading to increased risks for diabetes, depression, and cardiovascular disease. Time perception is another marvel. Dopamine, the neurotransmitter associated with reward and motivation, also serves as your brain's pacemaker. When dopamine levels rise, your internal clock seems to speed up, explaining why time flies during enjoyable activities. Stress hormones like cortisol have the opposite effect, stretching subjective seconds into agonizing minutes during traumatic events. The stopped clock illusion demonstrates this beautifully. When you suddenly shift your gaze, the first image seems to freeze because your brain extends perception backward to compensate for the saccadic blind spot in eye movements. Aging alters these internal timekeepers profoundly. Children have faster circadian rhythms, their days literally feel longer because they pack more heartbeats, more breaths, more neural firings into each hour. By age 80, the SCN weakens, producing less distinct daily rhythms, partly why older adults often experience fragmented sleep. Cellular clocks also degrade, telomeres shorten until cells enter senescence, the biological equivalent of a clock winding down. Yet remarkably, some aspects of biological timekeeping remain precise into old age. The 90-minute REM sleep cycle, for instance, stays reliable even when other rhythms falter. Modern life wages silent war against our clock. Artificial light, especially blue wavelengths from screens, tricks the SCN into suppressing melatonin hours after sunset. Irregular meal times confuse peripheral clocks in digestive organs. Social jet lag, the discrepancy between our biological and social schedules, has become so widespread that scientists estimate the average person lives 17 years of their life out of sync with their internal time. The consequences are measurable. Disrupted circadian rhythms correlate with higher risks for obesity, cancer, and neurodegenerative diseases. Yet within this temporal fragility lies resilience. Your body's clocks can be retrained, not instantly, but gradually, through consistent light exposure, meal timing, and sleep schedules. Morning sunlight resets the SCN more effectively than any alarm clock. Scheduled fasting helps synchronize metabolic clocks. Even simple routines, a warm drink at the same time each evening, a regular walking hour, provide temporal anchors that stabilize biological rhythms. As you lie in bed tonight, consider the exquisite timing unfolding within you. Your pineal gland secreting melatonin like clockwork, your core temperature beginning its slow nocturnal drop, your cells preparing their nightly maintenance routines. These rhythms connect you to deeper timescales, the lunar cycles that influenced our ancestors' sleep before artificial lighting, the seasonal variations encoded in our genes, the evolutionary history written into every cycling protein. Your experience of time, the quickening of joyful moments, the crawl of painful ones, the strange elasticity of memory, all emerges from this symphony of biological clocks. When you recall your first kiss or a childhood home, you're not just remembering events, but the particular tempo of your body during those experiences, the racing heart, the quickened breath, the dopamine-flooded neurons that made certain moments stretch and others compress. But what happens when these intricate timekeepers confront extreme environments? How does the body's rhythm respond when gravity weakens, when days lengthen or shorten dramatically, when removed from Earth's reliable cycles altogether? That is the mystery awaiting us in the next chapter. Chapter 7. Frozen Time, the Edge of a Black Hole. At the event horizon, time slows to a whisper. A single second stretches into eternity. What would it be like to hover there, between moments, watching the universe speed forward without you? Imagine standing on the shore of a cosmic waterfall, a place where the river of time itself pours over an invisible edge. The water near the brink moves sluggishly, thick as syrup, while farther out it quickens to a torrent. This is the edge of a black hole, where gravity warps spacetime so profoundly that time distorts in ways no earthly experience can prepare you for. Your journey begins long before you reach this strange shore. From a safe distance, the black hole appears as a perfect circle of darkness, a silhouette cut from the starfield. As you approach, gravitational tides begin their work. If you were falling feet first, the difference in gravity between your head and toes would stretch you like taffy in a process physicists call spaghettification. But let's imagine instead you're in a magical ship that can resist the pull, allowing you to hover just outside the event horizon, the point of no return where escape velocity exceeds the speed of light. Here, time behaves in impossible ways. For every second you experience, years pass on distant worlds. Your signals to the outside world stretch into lower frequencies, their light redshifting toward invisibility. From an observer's perspective, your image frees at the horizon, dimming over centuries as the last photons you emitted struggle against the black hole's gravity. Yet for you, time flows normally. You could watch your entire life flash before your eyes while the universe outside accelerates in a blur of starlight. This phenomenon, gravitational time, was predicted by Einstein's general relativity. Near extremely massive objects, spacetime curves so severely that time slows relative to less curved regions. We observe miniature versions daily. GPS satellites orbiting Earth must adjust their clocks because time passes about 38 microseconds faster per day in their weaker gravitational field. But at a black hole's edge, the effect becomes extreme. At the event horizon of a stellar mass black hole, time effectively stops relative to the outside universe. The numbers defy intuition. Hovering just 1 centimeter above the event horizon of a 10 solar mass black hole, your clock would tick once for every 1.5 hours passing on Earth. Get closer, within the width of an atom, and that ratio becomes 1 second to 30,000 years. The mathematics suggests that crossing the horizon would freeze you in the universe's memory while you experience something else entirely. What lies beyond remains physics' greatest mystery. Classical relativity says you'd encounter the singularity, a point of infinite density where spacetime curvature becomes infinite and all known laws break down. Quantum mechanics suggests the reality may be stranger, with theories ranging from wormholes to other universes to holographic projections of information on the horizon itself. Some models propose firewalls of high-energy particles, others suggest you'd simply continue falling through distorted spacetime until crushed by tidal forces. Your biological clocks would rebel long before reaching these extremes. The human body relies on precise timing mechanisms, neural signals that take milliseconds to travel, heartbeats spaced by fractions of seconds, chemical reactions timed to microseconds. Near the event horizon, these processes would appear frozen to outside observers while subjectively continuing for you. Your circadian rhythms would decouple entirely from any external day/night cycle. Dopamine and serotonin fluctuations, the biochemical basis of your subjective time perception, would operate in a realm where seconds stretch into years. Black holes aren't the only time-bending objects in the cosmos. Neutron stars, the dense remnants of supernovae, also slow time significantly. On the surface of a typical neutron star, time passes about 30% slower than on Earth. The entire universe exhibits gravitational time dilation on cosmological scales. Clocks near the Big Bang ran slower relative to today due to the denser early universe. Yet black holes remain time's ultimate funhouse mirrors. Their event horizons represent what physicists call closed time-like curves, paths where time loops back on itself. Some solutions to Einstein's equation suggest that certain black hole configurations could form time machines, allowing travel to the past, though likely prevented by quantum effects. The Kerr black hole, a rotating variety, contains a region called the ergosphere where spacetime itself gets dragged around at relativistic speeds, potentially creating conditions where cause and effect could reverse. As you imagine hovering at this cosmic threshold, consider the ultimate time capsule effect. Any object falling into a black hole becomes imprinted on its event horizon due to quantum effects, a phenomenon called the holographic principle. In theory, every book ever burned, every civilization lost to history, every forgotten moment might be preserved in scrambled form on some distant black hole's surface, waiting for physics we don't yet understand to decode it. The experience would be profoundly isolating. Watch the outside universe accelerate, stars flaring and dying in seconds, galaxies swirling like paint down a drain. Civilizations rising and falling in the time it takes you to draw a breath. The cosmic microwave background, the afterglow of the Big Bang, would blue shift into invisibility as the universe's expansion appears to reverse from your perspective. Eventually, you'd witness the theoretical heat death of the universe, all stars burn. All matter decayed, in what subjectively feels like moments. Yet paradoxically, you'd also represent a kind of immortality. From your perspective, the universe's entire future would unfold before you crossed the horizon. You'd become the last conscious being to witness the cosmos before its final darkness, a living time capsule at the end of time itself. But what if time's strangeness isn't confined to black holes? What if quantum particles routinely perform temporal acrobatics beyond our perception? That revelation awaits in our next exploration. Chapter 8. The Paradox of Time Travel. If time is a river, could you swim upstream? What would happen if you met your past self? The universe has rules, but are they walls, or just gentle warnings? You stand before a vast hourglass, its upper chamber nearly empty. Most grains of sand have fallen, your childhood, your first love, moments you can never relive except in memory. But what if you could flip the hourglass? What if you could gather those scattered grains and return them to where they began? The fantasy is ancient, but the physics is startlingly modern. According to Einstein's equations, time travel to the past isn't strictly forbidden. The universe might allow it, with conditions so strange they defy everything we know about cause and effect. The possibility first emerged from Kurt Gödel's 1949 solution to Einstein's field equations, a mathematical description of a rotating universe where spacetime loops back on itself. In this bizarre cosmos, you could travel forward along a curving path that eventually returns you to your own past. While our universe doesn't rotate this way, the discovery opened the floodgates for other theoretical time machines. Wormholes, Einstein-Rosen bridges, as they're formally called, could connect distant points in spacetime. With exotic matter, which has negative energy density, keeping the throat open, a wormhole might link different times as easily as different places. Cosmic strings, these hypothetical spacetime defects, thinner than an atom but with the mass of a mountain range per inch, could create closed time-like curves if two strings passed near each other at relativistic speeds. Tipler cylinders, a massive, infinitely long cylinder spinning near light speed would drag spacetime around it so severely that circles in space become loops in time. The common thread? Extreme warping of spacetime geometry. Time travel requires bending the fourth dimension into a circle, creating paths where future and past connect like points on a Mobius strip. But the universe seems to guard its chronology. The Novikov self-consistency principle suggests any time travel actions must create consistent histories. You couldn't change what's already happened. Kill your grandfather before he sires your parent, and the gun would jam, your hand would slip, some quantum fluctuation would intervene. The past resists alteration like a river resisting reverse flow. Quantum mechanics adds layers to the paradox. In 2019, scientists simulated time reversal for a quantum computer, sending a qubit state backward like rewinding a video. Some interpretations of quantum mechanics allow for retrocausality, where future events influence the past through delicate quantum correlations. The transactional interpretation even posits that quantum events are settled by offer waves moving forward in time and confirmation waves moving backward. Your body would face bizarre challenges in temporal transit. Traveling near light speed to reach the future, per special relativity, demands impossible acceleration. Every pound of your mass would require infinite energy to reach light speed. Wormhole travel might expose you to tidal forces or quantum fluctuations that scramble your molecular structure. And the sheer energy required to warp spacetime significantly exceeds anything our civilization could muster, equivalent to bending the mass energy of Jupiter into the volume. Yet the most profound barrier may be informational. When Hawking considered time travel, he proposed the chronology protection conjecture. Quantum effects, like vacuum fluctuations at the mouth of a wormhole, would always conspire to prevent paradoxes. The universe might self-correct like a overzealous editor, deleting contradictory timelines before they form. Imagine attempting to meet your younger self. As you reach out to touch your own shoulder, quantum decoherence would blur the interaction. Your atoms couldn't properly interact with their past counterparts without violating unitarity, the quantum version of don't create or destroy information. The handshake would fail at some fundamental level, like two copies of the same file trying to overwrite each other. Time travel's psychological toll might be equally prohibitive. Your circadian rhythms rely on Earth's 24-hour cycle. Your cells age according to thermodynamic time. Even your memories, neural patterns shaped by cause-and-effect sequences, might unravel in a reality where effects precede causes. The very concept of you could dissolve in a world without immutable pasts. But perhaps the greatest insight comes from entropy. The second law of thermodynamics gives time its arrow, and any reversal would require reversing universal entropy, gathering scattered smoke back into a cigarette, unbaking a cake into eggs and flour. Even if spacetime geometry allows time loops, thermodynamics slams the door. As you ponder these cosmic constraints, consider their silver lining. The fragility of time is what makes it precious. The unidirectionality of cause and effect allows for growth, for change, for stories with beginnings and endings. In a universe where anyone could revisit and revise yesterday, nothing would ever be truly created, only endlessly edited. Yet mysteries remain. Quantum entanglements, spooky action at a distance, hints at connections transcending classical spacetime. The holographic principle suggests our 3D reality might be a projection of 2D information, including time as an emergent property. And some interpretations of quantum gravity allow for baby universes branching off from black holes, each with their own arrow of time. But if time can branch, if quantum particles can blur the line between past and future, what does that mean for now? Could multiple timelines exist simultaneously, all equally real? That revelation awaits in our next exploration. Chapter 9. The Eternal Present of Quantum Worlds. In the quantum realm, time may not flow at all. Every possibility exists at once, like a book where all the pages are open. Is time just a story we tell ourselves? Imagine standing in a vast library where every possible version of every story ever written exists simultaneously. Somewhere in the shelves, there's a tale where you turned left instead of right this morning, where dinosaurs still roam, where the laws of physics themselves are rewritten. This isn't fantasy, it's the quantum multiverse, a realm where time may not pass so much as spread, where the present is not a single point but an infinite landscape of possibilities. At the scale of atoms and particles, time behaves nothing like the steady river we experience. Quantum mechanics, the most precisely tested theory in history, describes a world where particles exist in superpositions, occupying multiple states at once until measured. An electron isn't here or there, it's both, and neither, a probability cloud hovering in mathematical potential. This isn't just microscopic weirdness, it suggests that time itself might emerge from something deeper, like temperature emerging from the chaos of molecular motion. The quantum clock that never ticks. Your wristwatch measures time in predictable ticks, but a quantum clock would tell a stranger story. In 2013, physicists constructed a clock so precise it could detect gravitational time dilation over a height difference of just 33 centimeters. Yet at the quantum, time becomes fuzzy. The Heisenberg uncertainty principle dictates that a particle's energy and lifetime are entangled. The more precisely you pin down its existence in time, the less you know about its energy state. Some interpretations suggest particles briefly borrow energy from the future to overcome impossible barriers, a phenomenon called quantum tunneling that powers the sun's fusion. The eternal now of the block universe. Einstein's relativity paints time as the fourth dimension in a block universe, where past, present, and future all exist simultaneously, like frames in a film reel. Quantum physics takes this further. Every possible outcome of every quantum interaction spawns new branches of reality. In this many worlds interpretation, there's no collapse of possibilities, just endless splitting. The you reading this sentence exists in a universe where these words appear, while another version of you stopped reading long ago. Time isn't a flowing river but a coral reef, growing in all directions at once. Time's missing arrow. The greatest mystery. Quantum equations work perfectly backward. Unlike the macroscopic world, where eggs don't unscramble, a quantum particle's evolution is time-symmetric. This led Nobel laureate Carlo Rovelli to propose that time is an illusion, a side effect of quantum entanglement. When particles interact, they create correlations that our brains interpret as before and after. In this view, the present is just a particularly rich knot of quantum relationships. The watcher changes the story. Your consciousness may play an unexpected role. In the famous double-slit experiment, particles behave as waves when unobserved, but collapse into definite states when measured. Some interpretations, like von Neumann-Wigner, suggest consciousness itself causes this collapse. If true, then now isn't an objective feature of reality but a process, the universe resolving quantum possibilities into classical reality through observation. Your midnight insomnia might be the cosmos hesitating over which version of tomorrow to unfold. The holographic present. String theory's holographic principle suggests our 3D reality, including time, is a projection of 2D information encoded on a cosmic horizon. Like a movie screen creating the illusion of movement from still frames, the universe might render time from timeless data. Your experience of a flowing present could be analogous to a character in a video game believing they're moving freely, unaware their world is generated frame by frame from underlying code. Biological time in a timeless world. Your body stubbornly resists these quantum revelations. Circadian rhythms, cellular aging, and even the pace of your thoughts insist time flows linearly. Yet quantum effects subtly influence biology. Photosynthesis uses quantum coherence to optimize energy transfer. Bird navigation relies on entangled electron pairs in cryptochrome proteins. Perhaps life evolved to amplify quantum time into classical experience, like a phonograph needle converting grooves into music. The paradox of memory. If the past exists eternally in the block universe, then your memories aren't recordings but excavations, retrieving data from a dimension where that first kiss, that childhood home, still vibrate in the quantum foam. Trauma therapists find this metaphorically true. PTSD sufferers often relive events not as past, but as an eternal present. Time's flow may be a neurological construct, a narrative we stitch together from quantum snapshots. The end of endings. In a quantum immortal universe, death might be an illusion. Quantum suicide thought experiments suggest observers always find themselves in branches where they survive, leading to the eerie idea that consciousness persists in some timeline indefinitely. More soberly, your atoms, governed by quantum laws, will persist for trillions of years, eventually scattering across light years as the cosmos expands. In the longest view, time may not pass at all, just as a completed jigsaw puzzle contains all its connections at once. As you drift toward sleep, consider this: your pillow, your breath, the faint glow of stars through your eyelids, all are quantum systems first, classical objects second. The solidity of now is a beautiful, necessary fiction, like a movie's illusion of motion. Tomorrow will arrive not because time flows, but because the universe keeps choosing new states from an infinite palette of possibilities. But if time is an emergent illusion, what does that mean for the universe's first moment? Could the Big Bang be less a beginning than a branching, one note in an eternal quantum symphony? That mystery awaits in our final chapter. Last lines. But if time is an emergent illusion, what does that mean for the universe's first moment? Could the Big Bang be less a beginning than a branching, one note in an eternal quantum symphony? That mystery awaits in our final chapter. Last chapter 10. The last tick of the universe. One day, stars will fade. Black holes will evaporate. Time itself may grow thin, like a candle burning down to nothing. But even in the end, there is a strange kind of peace, the quiet of a story well told. Picture yourself floating in the deepest darkness you can imagine, long after the last stars have winked out. The universe has expanded so far that galaxies are no longer visible, their light, stretched beyond detection, has faded into whispers of infrared. All that remains are the corpses of dead stars, black holes so ancient they've begun to evaporate, their once impenetrable event horizons leaking Hawking radiation in faint, quantum size. This is the far future, some 10 to the power of 100 years from now, when entropy has nearly reached its maximum and the cosmos has settled into a state of near-perfect equilibrium. Time still exists, technically, but without change or events to mark its passage, it becomes meaningless, an empty hourglass with no sand left to flow. The journey to this quiet oblivion follows a predictable, if unfathomably long, sequence. First, the stars will burn out. In about 100 trillion years, the last red dwarf, the longest-lived type of star, will exhaust its hydrogen fuel. The universe will go dark, leaving only white dwarfs and neutron stars to slowly cool over eons. Eventually, even these remnants will fade. Protons, once thought to be stable, may decay over unimaginable timescales, perhaps 10 to the power of 34 years, converting all remaining matter into radiation and subatomic particles. Black holes will dominate the landscape, growing larger as they consume the sparse remains of galaxies, only to shrink again as they emit Hawking radiation. The largest may take 10 to the power of 100 years to evaporate completely, their final moments marked by a flash of gamma rays, the last light the universe will ever produce. In this distant era, time itself may begin to unravel. Physicists like Julian Barber suggest that without quantum events or macroscopic changes, the very concept of time loses meaning. The universe becomes a static, featureless sea of ultra-low energy photons and neutrinos, drifting forever toward absolute zero. Some theories propose that quantum fluctuations could spawn new universes in the vacuum, a process called quantum tunneling, but these baby universes would be causally disconnected from our own, their timelines entirely separate. Others speculate about Boltzmann brains, self-aware entities that randomly assemble from quantum fluctuations, experiencing brief, illusory moments of consciousness in the eternal dark. These are not predictions so much as warnings about how poorly we understand the nature of time in such extreme conditions. Yet there is a strange beauty in this cosmic quietude. Just as a single note resonates more profoundly in silence, the universe's story becomes more poignant when framed by its inevitable end. Every act of creativity, every moment of love or discovery, gains significance precisely because it is fleeting. The heat death is not a tragedy but a completion, the natural conclusion of a narrative that began with the Big Bang. Your life, brief as it is against cosmological timescales, exists in the sweet spot of cosmic history, after the primordial chaos but before the eternal chill, during the narrow window when stars shine and complexity flourishes. As you lie in bed, consider the atoms in your body. Their hydrogen nuclei were forged in the Big Bang, their heavier elements were tempered in stellar furnaces and supernova explosions. For 13.8 billion years, the universe conspired to arrange these particles into the pattern that is you, a temporary eddy in the flow of entropy, a brief flicker of consciousness in the dark. When you die, your atoms will disperse, but they will persist, eventually becoming part of new stars, new planets, perhaps new life. In the very longest view, we are all stardust waiting to be recycled, our stories written in quantum fluctuations and gravitational waves. The last tick of the cosmic clock may never come. Time could stretch infinitely into the future, an endless, featureless plane where nothing happens. Or the universe might collapse back into a singularity, resetting the clock for another cycle. Some theories even suggest that time could break down entirely at the Planck scale, becoming granular like pixels on a screen. But these are speculations for minds far beyond our own. For now, we have the present, this fragile, luminous moment when time still flows like a river, when the stars still shine, when the universe is alive with possibility. And so we return to where we began, with you, lying in the dark, listening to your breath. The universe is old beyond comprehension, vast beyond imagining, but right now, it is yours. The past is written, the future uncertain, but this moment, this singular, fleeting now, is real. Cherish it. Good night.